All right, guys, welcome back to Love and the Physics with Mr. Goldthorpe. So, we're now going to continue with conservation of energy, but we're going to move on to what we call non-conservative forces. So remember, if we have a non-conservative force doing work on an object, then we can be convinced that the total mechanical energy will not stay constant all the way through. It's either going to increase or decrease. And when we have that kind of a situation, we have a new formula that we're going to be using. It'll be EM initial plus work non, which will be the work done by all non-conservative forces, is equal to EM final. So we're going to get comfortable with that equation soon, but I just want to go over a couple of really important details about work non. So if I called it also work F here, but you can call it work non. In the first case, what happens if the work happens to be negative? And a really good example, which we've already seen, is if friction is going against the motion. If we have friction involved, we see that when it's acting on this puck, it brings it to rest. And when it does that, the puck at the end will stay at rest. So all the kinetic energy it had at the beginning is lost. In other words, we lose energy due to heat and sound. I'll just put over here heat. Energy will be lost as heat. And as a result, this is going to cause the total mechanical energy to decrease. So whatever mechanical energy it had at the beginning, it will decrease as time goes on because it's lost due to heat and sound. Mechanical energy will not stay constant. So this is what happens when you have a resistive, non-conservative force. It'll cause a mechanical energy to decrease. But if you actually have a propulsive force, what happens if the work happens to be positive? So you apply a force, say a person applies a force over a distance, like this. Now that's doing positive work from a non-conservative force. And you can see at the beginning of this motion, there was no kinetic energy because the person has not been moving yet. But at the end, there definitely is kinetic energy. The energy has increased. So when the non-conservative force is positive, energy will increase. You're basically adding energy into the system and causing it to increase. So mechanical energy doesn't stay the same, it gets bigger and bigger and bigger. Good. So those are kind of our two different cases of what happens with non-conservative work. Let's now go right to an example and give this a try, this new formula for us, and make sure we fully understand it. So here we have an object that's sliding down a slope, but this one actually has a friction force acting on it all the way through. So this entire motion, there will be a friction force going against this motion. There will be a non-conservative force acting on it all the way through. And our job is to figure out what the average friction force happens to be. So notice we have beginning, we have end, and complicated stuff happens in between. That'll still be like a conservation idea. The principle that we typically use here is called the work, just make sure you spell it properly. It is the work energy equation. Now I'm going to briefly show you where this actually comes from. We have work equal to change in energy. So there's the work energy equation. But the work would be the work done by the non-conservative force, in this case friction. And the work done by a non-conservative force changes the mechanical energy of a system. So this is what the work energy equation is actually saying. But delta EM becomes EM final minus EM initial. And if you rearrange that, you end up getting EM initial plus work non is equal to EM final. So this is the equation that I illustrated earlier. And you can start right from here if you want to when you're solving, or you can derive it like you see here if it makes it more interesting for you, if it makes more sense for you. Okay, and let's list them out. I'll have to keep bouncing back and forth. I apologize for that. But if we list out all the energies, the mechanical energies again are kinetic energy initial plus potential energy initial plus the work done by, in this case, the non-conservative force, which was the force of friction, equal to EK final plus EP final. Now at the beginning, can you see this thing actually starts at rest? That means that there's no kinetic energy. We can see that it does start with height if we assume the bottom right here is your reference height, which is a pretty logical choice here. So there will definitely be height at the beginning, so there will be potential energy. At the end, there is speed, so there's kinetic, and it's at the reference height, so there's no potential energy. So there's kind of our list of energies on either side. And what we can do now is we can solve for the work done by friction. The work done by friction will simply be equal to EK final minus EP initial, or 1/2 mv final squared minus mgh initial. Again, I'm going to go over a really important point here before we continue. Can you cancel the mass? If you wanted to cancel by mass, you'd have to divide both sides by m. So that's every single term. And you'll notice they will cancel on the right, but it doesn't cancel on the left because there's no m on the left. So you cannot cancel the masses here. We need the mass, and that's why I'm giving you the mass in this question. So it becomes equal to 1/2. The mass of the object, we're told, is 350 grams. So 0.35 kilograms. The final speed was 2.5. Don't forget to square that. Minus 0.35, 9.81, and the initial height is 74 centimeters, or 0.74 meters. Do we expect the friction force to do positive or negative work? Well, let's find out. We discovered it's negative. It's negative 1.447 joules. So it does negative work, which should surprise us because the force goes opposite to the motion. Now let me just copy this. Copy. And let's paste that image right here. Okay, and I guess the question here is, well, what does that actually represent? If I told you that the work done by friction is negative 1.447 joules, what does that tell us? And the answer is, remember friction, it creates heat energy or thermal energy. So this is the energy lost as essentially heat is 1.447 joules. Now it's really important that you know this when you're doing your homework, that if I tell you the energy lost due to heat and sound, I'm giving you the work done by friction. Good. Now we're not looking for the work done by friction though, we're looking for the force of friction, the average force of friction. So we have another equation at our disposal, and that is the work done by friction is equal to FF delta D cos theta. All right. Now I guess the key thing here, just a couple of details. What is the displacement? Remember, displacement goes from start to finish. So from start to finish, this going down the slope, that would be the delta D, which is 115 centimeters. And for cos theta, You might be tempted to use the angle for the incline, but remember, that's not what theta represents. Theta is the angle between F and delta D, between the force and the motion. Because the force goes exactly opposite to the motion, you'll see the work is going to be negative. The work done by FF simply becomes equal to negative FF delta D. Remember, really, it's either going to be positive FD, negative FD, or 0. So don't use the angle of the incline. That's not what theta represents here. So we're just trying to solve for FF. So FF becomes equal to the work done by FF over negative FF delta D. The work done by FF is negative 1.447 joules. Oh, I don't know why I put an FF down there. So sorry about that. There we go. I don't put everything on the bottom. Over negative, and the displacement is 1.15 meters. Make sure you use standard units. And sig digs looks like 2, so I get about 1.3 newtons. And that's the magnitude of the average force of friction. So those are kind of our two equations we have at our disposal with friction questions. We've got work is equal to negative FD, and of course we have EM initial plus work non is equal to EM final. So I recommend you guys go and try to practice some questions that involve just friction or air resistance. And then you can come back and try the next one we do together. I'll see you then.